There's no homework, so you got that going for you. There will there be homework on Wednesday for you to do over spring break? When I give you a homework assignment that requires 2 full weeks? No, I would not. Uh, there was a midterm due this morning, and I saw everyone submitted it. That's great. So I will now have to dig through 11 midterms and grade them. And that's just a lot of fun. Let's take a detour this morning and talk briefly about computing ethics. So the ACM, many of you are probably members of the ACM. Some of you are probably members of the IEEE Computing Society. This sort of applies to them as well. But I wanted to call out the ACM because most professional organizations have a code of conduct for their members. And the ACM has one that was created in 1992. In 2018, which seems like a lifetime ago, but it was basically like a year pre-COVID, they updated theirs. They decided they really needed to a significant update to their code of conduct, their ethical guidelines, and they made a major revision to it. And at least one other organization, IFIP, has actually adapted the ACM's code to create their own. And there are a few others that are very similar that were updated. And a lot of this came about to capture what people thought were some general principles that had been missed earlier. And some of those were respecting privacy in there and avoiding harm. And so there was some general changes to it. The outline of it is over there on the right, and it may be worth taking a look at. There's a collection of case studies online. Like most things, we can give you a set of principles, but they're pretty abstract, and so sometimes it helps to put it in the context of specific case studies, and the ACM has done that, and those are available at that site. The preamble to it states that questions related to these issues are best answered by a thoughtful consideration of fundamental ethical principles, understanding that the public good is the paramount consideration. So they say, go use whatever set of ethical principles you have, but put the public good as the highest goal for what you're doing. So what are fundamental ethical questions? They don't give you any, but they sort of take the form of what you see here, right? Why am I doing this? What's my intent? Intent's fairly important, but certainly not the only aspect of an ethical consideration. What are the consequences to myself, to others? What are the short run and long run consequences of the thing that I'm doing? It's hard to think about the long run just because it's difficult to predict the future. Even if you're busy inventing it, it's still really difficult to predict the future. So, that can be challenging, but you should at least make an attempt to do it. What do I think the long run consequences of this action will be? Is it legal? That might be a worthwhile consideration. Is it consistent with ethical codes I've agreed to, like the ACM code or the IEEE code or Tennessee Tech's code of ethical conduct? Because maybe you don't want to get kicked out of those organizations, right? I mean, if it's legal, there can be, you could be fined, or you could potentially go to jail for it. If there are ethical codes that you've agreed to be part of an organization, the worst they can do is probably just kick you out of the organization. And unless you require professional licensing, like you are a therapist or you're a doctor or you're a lawyer, that's probably gonna not be tragic. But if you are a professional engineer or you're a speech pathologist or you're a surgeon, that can be pretty severe. Is the action consistent with my own personal moral code? You may have a moral code that perhaps it's one that you've adopted from a religion, perhaps it's one that you've invented yourself out of whole cloth, but is the action consistent with your own moral code? And then finally, how would you justify this action to others? If someone asked me, why did you do that? Well, I did that because of the following reasons. And the answers to the stuff above it should give you the justifications to give to others. All right, a few thoughts. This all arose because of what's considered to be the ethical crisis in computing. And there's a number of different places you can read about it. Everybody writes about it from their own different point of view. I picked on Zunger's article in the Boston Globe. Computer science faces an ethics crisis, and the Cambridge Analytica scandal proves it. But there are plenty more. If you search for ethical crisis in computer science, you'll find lots and lots of stuff out there about it. So what is the ethical crisis in computer science? Well, it primarily arises from two sources. The first one is applying AI decision-making to everything, right? But most notably, cases in which you can severely harm the welfare of people by making bad decisions. And those are things like criminal sentencing, loan approval, policing, self-driving cars, the list goes on and on. In all these cases where we're applying AI decision-making, we may have to make ethical judgments, or at least have the AI make ethical judgments, right? Should you go to prison for a longer sentence or a shorter sentence? Should we send more police to your area or fewer police to your area? Should we run over the kid in this lane as opposed to hitting the bus full of senior citizens? These are all things that we have to deal with here. And this is creating a bit of a crisis of how do you deal with systems, algorithms, where you may be feeding them prior data, and that data may have biases baked into them, which then turns around to generate biased decisions, which result in bias in those decisions in the world, which then feed more biased data back into the system. The other case where this comes up is mass data collection. So you have companies that may misrepresent or even hide their actions about collecting data, and then they turn around and monetize the data without your knowledge, sell it to other companies, and there are a number of concerns there, right? Facebook, as it turns out, knows a lot about who's sick at any given time and what their illnesses may be, and whether those illnesses have been reported to, for example, their insurance company, and whether there's a pre-existing condition. And there is at least one case of an insurance company searching someone's profile to find pre-existing conditions. So, how do you score that? Were you wrong to not disclose it to the insurance company? Was the insurance company wrong to I don't know, but these are concerns, and addressing these is part of why we find ourselves in what's regarded as an ethical crisis. As far as algorithm bias goes, I recommend this article from Vox. It's available online about algorithm bias. For privacy, well, I didn't recommend an article on privacy for you for that specifically because there are just a ton of them. But I would just point out that privacy is a fundamental human right from the UN Declaration of Human Rights. The US ratified that in '92 under the first President Bush. But the Supreme Court has decided that the Declaration can be used to inform law, and in fact, it is cited many times in court decisions, but it does not necessarily impose obligations under US law. Even so, a number of Supreme Court cases recognize a right to privacy as one of the unifying principles of the Bill of Rights. You have freedom of assembly and speech, and to be secure in your homes and your possessions. And a number of justices, Blackmun and others, have found a right to privacy underlying those. And basically in the US, the government needs a compelling reason to invade your privacy in most cases. And that compelling reason could be exigency, probable cause, warrants, and court orders. But for the most case, you have the right to privacy in the US, and you should feel, you should treat it like any other right? I mean, you shouldn't just let it atrophy. You should realize that there's a right to privacy, and you should help support that right. Is privacy dead? A lot of people like to say that privacy is dead and we should quit talking about it. But companies haven't stopped talking about it because they want privacy. They want to secure their own data and their own algorithms and their own trade secrets, and they want to secure your data. So if Facebook can't sell your data to lots of other people if everybody else in the world already has it. So there's a lot of I wouldn't say a lot, but quite a bit of privacy work that we see out there is funded by organizations that want to use that work to preserve their own data. So the data protection measures that a company might use in some ways are very similar to or even the same as the protections that we might use for individuals. So I would say that based on this, privacy is not dead, but the counter is individual privacy is dead. I would claim that that's not necessarily true either for a number of reasons. One is that there are people in the world who are currently being persecuted by their government or would be if facts about them that they have no control over came out. Right? There are people who are persecuted for an accident of birth, for deeply held beliefs that don't harm other people. And these people need privacy in order to be full contributing citizens of the world. And they just do. That's just a fact. The common argument is if you've got nothing to hide, you have nothing to fear. That is so widely debunked that that I'm not going to take a swing at it, except to point out that this always presumes the people that you may be hiding something from share your values and act in good faith, which is not. There's no reason to believe that's true. All right, so big data, basic privacy, the growth of AI, all parts of what's regarded as a crisis in computer ethics. All right, enough of that. Shift gears back and let's talk about semantic slicing, which is only a slight shift. It may seem like a drastic shift, but it's a slight shift. We're trying to invade the privacy of some code on our system and figure out what it's doing. And one way to do that is to throw away all the stuff we don't care about, right? Pictures of its family, all that stuff that it's got lying around. We don't care about any of that. We want to get down to brass tacks and find out what the code is doing in some specific instance. We've talked about slicing already. We did some basic slicing on some C code. We sliced on assembly. We did dynamic slicing where we assumed something about values in the program and did an execution trace and then sliced execution trace. And now let's take a look at semantic slicing. So we're going to go back to the first program we ever looked at, this little short snippet of assembly. And honestly, I can't remember where this comes from. This comes out of some piece of assembly somewhere. I forget where. It's something I wrote, who knows where. Sometimes it's useful to have a little snippet be compilable, right? I might want to turn a bunch of different tools at this little piece of code, and this little piece of code as it stands here is not readily compilable. So let's think about what we might do to make this compilable so I could use some of these other tools to analyze it. Well, the one thing to do is to add terminations at the end so it didn't just run off the end after that pop RAX. And so there we go. I'll just terminate the process. And that's the safest thing to do because a code snippet might not have balanced pushes and pops, and what's on the stack might be nonsense. And so if we try to return to some higher level process, it's probably not going to go well. So the safest thing to do is just say, you know what, just terminate the process right now. This one looks like it's probably balanced, which would be fine, but let's just go ahead and kill this off. Another thing is we need to do something about this call to opc. And there's a couple different ways we can go here. I could just declare it to be external at the top and then just never give it to you. And that's fine. I can still assemble the code. I just can't link it because I've got nothing to link the underscore opc to. And so I can't do that. So since I can't link it, and I would maybe like to be able to execute it, what I'll do is take the second option, which is actually the first option over here, sorry, and I'll just stub it out. So here's my opc function. It comes in and returns. Right, that's all it does. There's no need for all the stack frame stuff unless I really just want it. All you do is return. And is this what opc does in the real code? I'm pretty sure it's not, but it's good enough for us to get this to actually assemble and run. Another thing to do is we need to give it a start. So I'll just do that right up here, global start, underscore start right here. There's my code. It's looking pretty good. And then finally, I'll give a little line so my make utility can find it and build it. And here I'll actually assemble it and link it. If I had wanted to dynamically link it or try to do that, I might have a different thing here. I'm going to assemble and link it. If I just wanted to assemble it, I have a .o file I could analyze. That'd be fine. I would just use that line. And at this point, we can build it. We could load it into a debugger or into a assembler like Ghidra, and we could perform whatever analysis those tools give us. And that might be really useful for this little piece of code. It's a smaller piece of code, we probably don't care. But for a larger chunk of code, we would almost certainly want to know what it does, and we want to be able to use some of the analysis tools that we get from Ghidra and others. All right, so back to the code the way it was, and let's talk about slicing. And we're going to slice on semantics, so we need a semantics from somewhere. We could use the K framework. We could invent our own semantics, which would be a terrible idea. Use something someone already has. But let's go ahead and use P code as our semantics from Ghidra. So P code is a simple programming language that we looked at 2 classes ago, I think. And so we can go ahead and go into Ghidra and generate the P code for this. And in fact, now that we've created an executable version of this, that's really easy. We just open that executable up in Ghidra, enable P code, and then just copy out the P code and paste it into a slide like we've done here. And so you wind up with something that looks like this. And so for a simple instruction like increment a register, you wind up with all of this complicated stuff. And for a complicated thing like calling opc, you wind up with a few things. Just further evidence that assembly is annoying. So increment RAX, we note that RAX gets the integer add of RAX and an 8-byte 1. That's what that little 1:8 means. It's the one that's 8 bytes long. We set the overflow flag, the sign flag, the 0 flag. We have these guys. These are temporary values. And we will set them and we can use them as we see fit. This is an 8-byte value. This is a single byte value, and this is a single byte value. And then, of course, the parity flag is set to be true if this temporary variable is equal to 1. Where did that come from? It came from right there. Oh, sorry, it came from right there. It was built by taking the previous one, ANDing it with 1, taking the previous one, generating pop count, which you can go look up for it, and then finally taking this one and ANDing RAX to remove the last byte. So there you go. Load effective address. It's pretty simple. We take RAX, multiply it by 8, and then load it into RCX. Is that what happens over here? Sure enough, we have a temporary that's set to RAX times 8, and then we make a copy of that temporary and load it into RCX. For push, we have to make a copy of the thing we're going to push. We subtract 8 from RSP. We store in RAM at location RSP the temporary thing we copied. And so you'll see this is how all these little guys work. Something worth pointing out is that what we get back for opc is true, but not helpful. What does call opc do? Well, it goes ahead and subtracts 8 from the stack pointer. It stores our return address, the address of the next instruction, current value of RIP, in RAM pointed to by RSP, and then it does a call into RAM to the location of opc, which happens to be this in my little stub program. That's all true. That's not untrue, but it's missing some stuff. In particular, even my little stub does something that's not captured here, which is it returns. And when it returns, it will then add 8 to the stack pointer. So if I just read this as it is and said, this is what it does and nothing else, then I'd be wrong. This would tell me, blah, 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 subtract 8 from the stack pointer, and I would go forward with that modified version of the stack pointer, when it's very likely, though not guaranteed, that the stack pointer is actually not modified by this. When I zoom out, right, when I take a look at this, what happens in this instruction, I expect the stack pointer to be returned to where it was when I started, because the stack pointer is a callee saved register. And so I don't expect it to be modified by this. I expect it to come back with the stack pointer right where it was. So the semantics for call, it would be fine if I knew what call did and I put all of that information in here, but I don't. So the best thing to do would be to remove it. And that's what we're doing here. We're just dropping what the call does. So here are our reduced set of semantics without the call. And we need a slicing criteria. And the slicing criteria is RAX at the end. Okay, so we're going to know what is RAX at the very end here. And we can find that in the way we usually do. So with the set of things we care about is just RAX. We go back a line. And remember, this is sequential. These lines of P code are sequential. So really, I would go back to this line and say, does it modify anything I care about? And the only thing I care about is RAX. Does it modify RAX? It does not. So the set of things I care about does not change. It remains just RAX. Since it didn't modify anything I care about, didn't make any changes to it, I'm going to discard this line. I don't need it. So then I will have my set of things I care about, RAX, and I'll go back to the previous line, one before that. Does it modify anything I care about? Yes, it does. It modifies RAX. RAX is an L value. What are the R values? The R value is RAM at position RSP. Okay, so I'm just going to write RAM RSP over here. I don't have RAX anymore. I removed it because it was overwritten. It was overwritten by this. So the set of things I care about is now just this thing in RAM. And so we keep working back the same way, right? We walk back one more and we'd say, is anything I care about modified here? Yeah, actually there is. The stack pointer, right? This expression depends on the stack pointer. There's the stack pointer being modified. I am adding 8 to it, which means that the value I care about before this instruction runs is RSP minus 8, right? Because then I would add 8 to it and I wind up with RAM RSP. So there we go. Now I've got this value. And I would look and say, is there anything I care about here? Well, no. There's not an L. There's not, none of the stuff I care about is an L value, right? The fact that I have loaded from RAM and RSP, that's not relevant. That's not even what I care about. I care about RAM RSP minus 8. But even if it's for RAM RSP minus 8, I wouldn't care because it's modifying RCX, which isn't something I care about. So we keep walking backward like this, and we just zip back through here. And for some of these, we'll find that we do need something. RAM RSP minus 8. We look at this one up here. It modifies RSP by subtracting 8 from it. And so the thing we care about prior to the subtraction must be whatever the value of RSP is plus 8. And so I would take the minus 8 and it just becomes RSP. Up here, it's RAM RSP. And sure enough, there it is. It's an L value. It's being overwritten by this temporary value. So that becomes the set of things I care about. That's the only R value, so that's the only thing left in here. And I continue back. Nothing I care about is mentioned here. So that state doesn't change. Now, this is being modified. The thing I care about is an L value. The only R value is RCX. So that becomes this thing I care about. And I would just keep walking back. RCX is mentioned here. It's this. That becomes the thing I care about. It's here. It's a copy of RAX times 8. So my R values are RAX and the constant 8. So I just put RAX over here. And then finally, I can work the rest of the way up. I care about this one, right? I don't care about this. I care about these. Here, something I care about is being modified. And so I want this line. And so what I've done is, as I've gone along, I've highlighted the lines that I need. And those are just the ones in yellow. So here is my original P code program with the slice I want highlighted in yellow. And when I reduce it to just those lines, that's what I get. I get this little sequence right here. Now these temporaries are a bit annoying. So I'm setting a temporary here, and then I'm immediately copying it here. I'm setting it here, I'm immediately copying it here, and they're not mentioned anywhere else. So let's get rid of them. And so we just substitute for those. And here is my little program. And remember, this is sequential. So do this, then do this, then do this, then this, then this, and then this. This is a little program in the P code language resulting from the slice. What does it do? Well, let's convert it to static single assignment. We've had good luck with that in the past. So we do that. This would be the initial values are zeros. So this would be 1. There's RX1 to set RCX1, RCX1, RSP0, now RSP1, RSP2, so on. So there we go. Basic static single assignment. And now we can actually do back substitution. So if I want to know what RAX is at the end, it's not, we've already got the slice. We generated the slice. We solved that problem. Now I'd just like to know what RAX is at the end based on the slice I've got. So RX2 is load RAM RSP2. So I plop that down here. And I want to substitute for RSP sub 2. That's here. And it's this expression. So I just drop it in there. And what's RSP1? Well, it's this. So I just drop that in. And notice I have take RSP0, subtract 8, and then add 8. So RSP0 minus 8 plus 8 is just RSP0. And this is true, even if things are signed, even if there's wraparound, it doesn't matter. This is how the integer math will work. So I can say this without having to worry about, do I overflow some register or something like that? Doesn't matter. That's just how it works. If I wrapped around, then I wrap back around. So load RAM RSP0. Okay, load RAM RSP0. And what is that? Well, my claim to you is that's RCX1. And my brain is temporarily fried this morning. Load RAM, right, because of this. Sorry, my brain is shot this morning because of this long problem with my daughter's insulin pump. So right here, I actually know what is stored in RAM RSP0. It is, in fact, RCX1. So I can replace RAM RSP0, which is not RSP0 by itself, but RAM RSP0 with RCX1. And there it is. What's RCX1? I go up here. That is this guy. So I just substitute it in. And what is RX1? That's this guy. So I just substituted it. So what is this? This takes RX0. It adds 1 to it. And then it multiplies that result by 8. And there you have it. And so we might conclude that the total effect of this code is that RX at the end is RX at the beginning plus 1, that quantity, multiplied by 8. And there you go. That's just what it is. We take the initial value of RX, add 1, multiply it by the length of a pointer, and do that for some reason. So we can actually reduce the entire program to a single line of code, for at least the part we care about, which is this: load effective address, REX with this. And if that was all we cared about at runtime, we might even go in and patch the code so that it had this in it, and we could then observe the effect of that. But there you go. So we started out with a piece of code. We converted it to P code so that we could do more fine-grained slicing. A lot of stuff, let me go back a bit, a lot of stuff went away. Here was the original code. It packages up a lot of things that go on, flag information, stack information. P code makes a lot of it explicit. We then sliced on it and wound up with a fairly small slice that represents the same semantics as the original code. And then we work backwards to figure out what it does. So all of that works just great if you have a ready source of semantics lying around that you can use. What if you don't? Is there a, we finally need to get down to having a specific algorithm to apply to this. So if we don't have a convenient semantics, how far can we get with slicing assembly? And I'm going to call that naive slicing. And here's my naive slicing algorithm. So we have a slicing criteria, we have a variable and a location. And D, capital D, is what we'll call the dependency set immediately before each line. So at line N, I want to know what the variable V is. And so I'm going to say the dependency set immediately prior to line N is just the set containing V, which is the variable I want to know when I reach line N. So there we go. That's my first crack at a dependency set. Read I will be the set of variables that are read at line I, basically the R values. Write I is the set of variables that are written at line I. That's basically the L values. So in assembly, we can't break apart the instructions into pieces. And this has the consequence that if I need to know anything that is an L value in an instruction, like maybe the contents of a register or just a single flag, then I have to know all the R values for that instruction. So when I could break them apart using P code, I could just talk about the parity flag or just talk about the register. But suppose I need to know the 0 flag that's the result of an operation. Well, then I need to know all of the R values for that operation, right? Because I don't necessarily know what the 0 flag exactly depends on. And I may have to keep all this stuff around that I could otherwise get rid of. All right. So here's the algorithm. We set up the slicing criteria just like I described. The dependency set immediately prior to line N is the variable I care about at that location. And then I walk backwards. So from line N -1 back to 0, I do the following things. And none of this should be a big surprise to you. I go and get the variables in the depends set. Initially, that's just this. And I see if there are any L values for the current instruction. And I remove them from the set if they are, right? I drop L values. So W is my set of written registers or variables. And I intersect that with the dependency set. So this asks the question, what is written by the current instruction that I care about? And I'll get back a set, and this set might be empty. So I take my dependency set at location I, it's my loop index, and I set it equal to the dependency set at the next line, I +1. First time through, that's going to be this guy. And I subtract those. So I subtract the L values that are actually written by that line. So I'm discarding it from my set. If any variables we care about are written, then add all the R values to the depend set. So now W is the things that are written that we care about. If it's not empty, then to the dependency set, I add all the things that are read. These are all the things that the value could depend on. Whether it really depends on them or not, I don't know. I can't break apart the semantics to find out, but these are all the things it could depend on. Finally, if nothing we care about is actually written, then we don't need the line and we discard it. So we compute two things here. We're computing the set of, if we start out with this as our set of live variables, we're actually computing the live variables at each step. And if nothing we care about is mentioned, then we discard it. So this is doing both live variable analysis, which should look very similar to you, and also slicing it by discarding lines we don't care about. So there we go. W is a set of things that are written that we care about. D is the dependency set. And we're discarding the line when W is empty. So what does this actually look like? Let's go back to the program we've been picking on, this little guy here. And well, this is a little bit different one. Sorry, this is a different snippet. This is from user bin Python 3.7. So not the most recent version, but it was the most recent version when I made the slide. And we see at the end a jump to R11. And there are tons of these little jumps throughout code you'll look at. And we might like to know, where does that go? Where's R11? So just looking at this in assembly, I would look right here and I would say, oh, it's going to something stored here at this location based on R10. What's R10? It's here. So I have to go back and see what RBP plus 8 was. Looks like a local variable because I'm adding to RBP. All right. But let's actually go through the process and try to figure this out in a more formalizable and more automatable way. So at each line, we'll ask, what are the variables in the live set depend on? And if it's in the live set, we'll remove it and then add it. So you'll follow. So here we go. I've got the code over here. I've got read here. These are the things that are read. These are the things that are written. And here's my dependency set. And I have initialized it to R11 because that's what I care about at this last instruction where I jump. So this means I don't care about the value. I care about the value of R11 immediately prior to line 7. All right. So R11 is basically live on the arc from this pop to this jump. Another way to think about it. Okay. So let's see what this would tell us to do. This would tell me to take R11, which is my dependency set, intersect it with the set of things that are read, that are written in the previous line to get W. And this set intersected with this set is empty. So there's nothing else for me to do. And in fact, that line can be discarded. So let's go ahead and formalize that. W is the right at line 6, which is R12 and RSP. I intersect that when drop the RSP here for some reason. And I intersect that with the set of things I care about, which is R11, and I get the empty set. And my dependency set isn't going to change because W is empty. And so there's no change to that. And because W is empty, I also can discard the line, which I've indicated by graying it out right here. And so we walk back another step, R11, and I intersect it with this. And again, it's empty. So this turns out to be true for both of these, right? R11 intersected with this is also empty. Now it changes. R11 intersected with the right set up here is R11, right? So the dependency set intersected with the right set. I actually have an L value I care about, it's R11. And so what I want to do now is add these to my dependency set. This gets removed because it's an L value, and everything over here gets added. And I keep the line because W is not empty. And so I should see, sure enough, there it is. There's a set of things over here, copied over here. These are the things I care about immediately prior to this line. And it's all formalized over here. I keep this line. So then I take a look at the stuff that's in here. I intersect it with RDI, and there's nothing in there. So that line gets discarded, and I keep the set the same. I intersect this with this one. Oh, this is in both. So R10 appears in both. So it's going to get discarded from the set, and all this stuff is going to be added. And so I do that. R10 goes away, and this and RBP get put in, and I keep the line. And I'm done. I work my way back up, and this is the set of things I care about immediately prior to this line. And there we have it. So we're left with just 3 lines, and they set the value of R11 prior to the call, and we can work back and figure out that it should be this. The base pointer plus 8, which again looks to me like a local variable, plus in this case, it turns out to be 48 from here. And so we take the address off the top of the stack, add 48 to it, and find the address of that location and jump to it. I guess that's what that's doing. Odd thing to do, but that appears to be what the code is doing. All right. I think we have reached, yeah. Whew. I'm going to let you go really early because I have a combination of meetings and general catastrophes that happened over the weekend, and I'm going to go deal with that. The next time we meet, we're going to go over the midterm. So I'm going to walk through it and we're going to talk about it. This avoids starting Mycroft either today or on Wednesday, which I think you'll agree would be good once you see it. It's not a good time to start it and then go off to spring break and then immediately forget all of it. Mycroft will actually, it'll be a paper I'll give you that you can read. It's about type analysis, and it'll take us probably 2 classes or to get through that and understand what's going on with Mycroft.